I just had an epiphany. For all my life, I've been wondering how crackers are able to patch software such that you can get access to some premium functionality without paying. I didn't get how it works. But somehow, this morning, it all clicked together. We've been doing so much different stuff on this channel, programming in C, some reverse engineering, and learning that all those different topics. And suddenly everything clicks together and cracking appears so simple. Let me show you what I mean. In this episode, we will have a look at a very simple password-protected C program that we coded in the last episode, by the way, for another demonstration. And instead of reverse engineering the password and spending a lot of effort in understanding what the how everything works in the compiled binary, we can just crack it. Let me show you what I mean. So let me just grab the source code that we coded in the last episode. It's this login C program. And it's a very simple program. It's just a main method. The program stores an expected password in memory, and it prompts the user to enter a password. Then the password is entered, and then there's a string comparison between the entered password and the expected password up here. And if the entered password matches the expected password, boogeyman, then the user gets a message success, else it's a failure. So it's super simple. It's just a check for a valid password. Now, if we compile that file, we get this executable down here. And let's execute it, and let's say we enter a password, for example, zebra, and we get a response that this is a failure because the password is wrong. Now we can also do this with different passwords, and we can just keep guessing forever until at some point, through some effort, for example, brute forcing the password or reverse engineering the binary, we get access. Boogeyman. Now, reverse engineering in this case is super simple because the password is just stored as part of the compiled binary, so it must be inside the compiled binary because it's inside the C source code. And let me just quickly show you how to find it. If you just object dump the binary, and then if you skip to the correct section, the row data section here, then you can see there's the password. Now, of course, if the password is some character combination, let's make it a bit more difficult, such that this example is it doesn't look so stupid. Let's say the password is something like this. It looks like hexadecimal, and we now basically have no choice, or we have no easy way to determine it. We already know what the password is, so it's easy to find. It's this string right here. This plus this is the password. But if we didn't know the source code, this would be very, very hard to reverse engineer. So also, we don't know if that is even the password. It could be XORed, for example, or obfuscated in memory somehow. All right. So now reverse engineering becomes harder than with a simple clear text password. And I can't even remember the password in my head, so typing trying to type something in the login, I don't know, would just fail. Yeah. So let's say as a reverse engineer, as an attacker to the system, we say, guessing the password is too hard. Now, if all we need is to get access to the system, then we don't even need the password. Of course, knowing the password is somehow the elegant way to enter the system. But if you just want to enter by force, you can just break in, and that's what cracking is. So, as you all know, the source code, the C file, login.c, this is written in C code. But when you compile it to this executable, it's a so-called ELF binary. This is a file format for compiled files. And it's just, as I just said, it's just binary. And using objdump -s, we can dump all the sections of the binary to the console. Now we can see all the values that reside at the different memory locations. For example, for this section here, the raw data section, at address 2000, this is a hexadecimal address, hence I'm not saying 2000. Those values are stored in memory. And then somehow the kernel or CPU, some low-level system component understands those as those values here. Well, this is a bad example because those are fixed constants. But those values here, they contribute to the code, and some sections, I think the text section, yes, this section down here, this is the actual code. So this is the compiled assembly stuff. Now, technically, since we know that the assembly must reflect the source code, and also without knowing the source code, of course, we know from executing the login executable, we know that there's a request for the password, a prompt for the password, and the user enters something. And then there's a check for the password, and then there's a failure. So there is some logic. There must be some string comparison, and there must be some if-else. This is just simple logic. Yeah. And from the object dump, we don't get that much insight because for us as humans, it's very, very hard to read this text section, which contains the compiled code. But somewhere in here, there must be this if-else instruction. And if we can change the right instructions here to print the success for any password entered, or for, let's say, to just flip the condition. If a wrong password is entered, then the user gets access. Then we have patched and cracked the program. So we just have to surgically, like a surgeon, understand the instructions here and change whatever individual instruction is the if condition that checks for the password. And then we should get access. So let's try to do that. Now, objdump is not very helpful because it's just printing all the binary data as hexadecimal to the console. It's a very useful function, but it's not good enough for determining which exact instruction to change. And for that, we can use we can still use objdump, but not the -s, but -d. And -d does, let me show you, -d it disassembles. It displays assembler contents of executable sections. So objdump knows which sections contain assembler code and then displays those to the console in a disassembled way in assembler. Okay, so let's disassemble the login. And as you can see, there's a lot of stuff here that is, it's still the same file and we have all those values here at the different memory locations, but in the right-hand columns, those instructions here are translated to assembler. So now we can check the main method and try to understand where the expected password is checked and compared with the entered password. So let's go down, and here we can see there's a call to string compare. String compare is, let me just search for that string compare. This is referenced and I think linked from the standard library. So this is just a function in assembler as far as I understand with my very, very, very limited assembler knowledge. So this is the function call that we are looking for, the string compare. So let's go up again. This is the main method. And let's go down until we see the string compare. We even see here in the disassembled code the string expected password. So this is referencing the expected password which resides in global memory. I don't know exactly why it is stored as clear text here, but it seems to be. Maybe because it's a global variable and it has to be referenced by some string. I don't know. I know this seems to be just a comment, but the comment contains the name of the variable. Well, but it's a good hint for us. But going back to the string compare instruction, as you can see, the string compare instruction is followed by a test instruction. And let me just open a browser so we can look up the individual instructions. Assembler test instruction, or assembly test instruction. And as you can see here in the x86 assembly language, the test instruction performs bitwise and on 2 operands. And here we are comparing the EAX register with the EAX register. So this is just comparing EAX with itself. I don't know exactly how this is supposed to work, but this is basically, to my understanding, this is a test that will always evaluate true. Wait, test EAX, let me just look that up. The point of test EAX. So this, I'm not the first one wondering about the point of that. Some x86 instructions are designed to leave the content of the operands registers as they are and just set unset specific internal CPU flags. You can think at the ZF, the 0 flag, as a true false Boolean flag that resides inside the CPU. So this seems to be the resetting of some flag. In this particular case, the test instruction performs a bitwise logical AND and discards the actual results and unsets the 0 flag according to the result of the logical AND. If the result is 0, it sets the 0 flag 1, otherwise it sets it to 0. So this seems to be just setting a 0 flag for some internal CPU details that I'm not too familiar with. Okay, but there is this call to a function string compare, and then there's this test instruction which is there for some CPU specific reason as far as I understand. And then there's the JNE instruction, and the JNE instruction x86 and JNE is a let me search for it, is a jump if not equal. So this is the actual if instruction. And this refers to this 0 flag. So maybe, yeah, so I don't know if that is a condition for this to be happening or not. It seems that the jump if equal uses 0 flag 1 and the other one uses 0 flag 0, but I don't think it's relevant. But what's important is this is a jump instruction, jump if not equal. It has the opcode 75 or 75 in hexadecimal. And this matches what we see here. So this is the jump if not equal function. And this is the opcode. And the jump happens to the address 1214, and 1214 is something down here. And here the code somehow continues. So a comparison between the inputs, between the passwords is done here. And then there's the jump if the inputs are not equal. So if the input, there's a big chance that this is the check that actually checks if the input password is, well, not equal to the expected password. Then we jump down here. But if it's equal, then there's no jump, and we continue with this code, with this LEA instruction, then this call Q instruction, and it's a function call that puts a string, put S is a string printing function to some file descriptor, and I think this is probably printing to standard out, and this is probably the printout of the success statement, and it's loading effective. This is loading the memory from this address, and this is probably the success statement. 0xe1c. Let me just check that. Let's go back to the other object dump and search for E1c. And I'm not sure about that syntax here. E1c. Let me just search for the success string in the in here. This resides at a different memory location. Okay, forget about it. I don't understand the syntax. But what's most important now is, and let's not waste too much time here. Let me just disassemble again. And here's the main method, and going down, this is the jump if not equal instruction, and if not equal, we jump down here somewhere, and if it's equal, we jump here, and well, we just continue and put a string to the console. Now, of course, telling all of that is super simple because I coded the source code myself, so this is just a super simple guess here. But now comes the fun part, and that is the core of this video. Now, to crack this, all we have to do is change this individual instruction here. And as you remember, this is the jump if not equal instruction, and it has the opcode 75. So this is the code that the CPU will understand. And if the CPU sees this value in memory at this location right here, then it knows, okay, now the next instruction is a jump if not equal instruction. However, if there was a different opcode, for example, this one, then it would only jump if it's equal. So this would mean that, well, here this jump if not equal, if the password is not equal, it jumps to the failure method, to the failure printout. But if we change this to jump if equal, then it will only jump to the failure if we enter the correct password. So we just flip the logic, and only if we enter the correct password, we jump. And in any other case, if we just get the access to the system, we just get a success. And this would be reversing the logic and giving us access to the system. Now we just have to know how to change this 75 here. I can't just edit the file using a text editor such as Vim, because here I have no idea what location I'm editing. This would be horrible. It would be possible probably somehow if I know what I'm doing and I just count the memory locations manually by hand and then I change some individual spot here inside the file, but that's stupid. Let's not do that. There's a dedicated tool for that that's called hex edit. And we can provide a file name, and we want to edit the login binary, and that's it. Let me just give this a bit more space for you. Just like so. Okay. And as you can see, the hex edit, we can also pass it as input argument directly. The hex edit prints the memory locations starting at 0, and then the values at those locations, and then those values here converted to ASCII characters, so we can actually read a bit. That right-hand column is just for our convenience. It's not strictly necessary. The left-hand column is very necessary because this is the location in the binary and this is the value in the binary. So what we can now do is, using the arrow keys, navigate up, down, left, right, and we can just change something in here. For example, we can change this E, which would be this, which would correspond to this 4-5 here. This is the first character, the 7F, and then the 4-5 is the E. So let's just change this to 4-6. And as you can see, the E changed to an F. And using the backspace, we can undo that. And yeah, and if we press Ctrl X, we can access the application. And if we did a change, let's say we changed this to an 8, now we have this HLF here. If we press Ctrl X, it asks us to save the change, and we can press yes, no, or cancel. I'll do no and open it again. So this is now the unmodified file. And now what we have to do is we have to find our jump if not equal instruction here in this file. And of course, the clever way to do it is to not search it manually, but let's exit the application and let's go back to our object dump disassembled assembly code. And here, let's jump to the main method and locate our jump if not equal instruction with the opcode 75, and it is located at the memory address 1204. Okay, let's remember that and let's go into hexedit login. And here we can just jump using the enter key to the new position 1204. And now the mouse or the cursor is located down here, right at the 75. I hope you can see it, it's here. And now we can change that to whatever else we want. Now, just for a quick recap, let's remember that we don't have access to this login binary. We can enter anything, let's say house failure, mouse failure, dose failure, love failure. So we can't access whatever we want to access here. We can't log in. Now, if we change this and if we change the opcode from 75 to from 75 to 74, this changes the instruction in the disassembled code, or not in the disassembled code, in the actual binary. And now we can Ctrl X, save the change using Y, and let's test the login again. And let's enter the same passwords that failed here and see if we can now access the system. Mouse, success. Dose, success. Love, success. It's all a success now. And that's the power of patching, cracking, disassembling, understanding the assembly code, which I don't really know that much about, but this is so awesome. This is probably a huge rabbit hole that allows you to just get access to anything you want. Now, remember that the actual password to the login file is quite complex. It's this one here, and reverse engineering it would probably be hard. I know in this example it's easy because it's part of the memory, but in general it's hard. And you can't really guess this password. But by cracking, you completely circumvent the matter of trying to find a password. You just change an instruction and get access through that. So just patch whatever binary you don't have, you want to have access in, and have fun. So now it accepts any password that we enter here, and it's super nice. Yeah, and that is how cracking works at the most basic level. Just surgically changing individual instructions, and the result is super pleasing in my opinion. If you enjoyed this video, then stick around and see you next time. Bye.